Good morning, guys. We are doing lab 13 for you today. I hope you university physics students did read the lab. I already posted in Blackboard. Okay, if you read it once, you will see how interesting is this lab. It has part A called simple pendulum. Okay, and it has part B. It's called simple harmonic motion. Okay. We'll take a break for a minute and then we'll start taking data. Thank you. Okay, student, time to take data. Okay, part A. Okay, so we create a pendulum. You can see this is 50 gram weight on a string, and the mass of the string is negligible compared to the mass. Okay, so this is fixed length. We are only going to see the mass dependent of the period. Right? Okay. So remember, so this is constant, 50 gram constant, and the length is going to be 0.61 meter from the hinge to the center of the ball. Okay. So all we're going to change the angle and look at the period. Okay. So you have look at your data table 12A1. If you look at first column, experimental value of the period, then you'll calculate period theoretically, okay, from period equals 2 pi square root L over M, okay, calculate that and then find the percent error. That's what in table 2A1. Okay, so let's start. Okay, we're going to take 10 oscillation, okay, and we'll record the time, okay, and you divide the time by number of oscillation, which is your period. We'll maintain, here you go, time, so we'll start time and then we'll take the, okay. So here you go. So number angle 5, okay. So here you go. So here we're going to use a protractor, okay, put it like this, okay, 90, so I go to 5 degrees, okay, then you go, I'll start time, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's like about 1.5 second. You understand? To divide the time by 10. Okay. So next one is 10 degree. Go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this time is about 1.51 second for one oscillation. Okay. So here you go. Reset. Next one is 15 degree. 10, 15. Let it oscillate. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So again 1.153. Okay. And then 20 oscillation.
Yep.
Okay. Let's do for 20 degree. Here you go. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's like 1.5 6. Okay, you understand, the time here it says 1562. Okay, divided by 10 is 1.5 second per oscillation, which is the period by definition. Okay, now 30. Okay, so from 20 we're going to 30. 30. I'm holding it. Okay. Two, 3, 4, 5, 6, 7, 8, 9, 10. So it's like 1.54 1.54 second. Okay. Now the last one is 45. Okay, I'm holding it. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so which for 45 is like 1.56 second. Okay, and then the last is 60. So 10, 20, 30, 40, 50, 60. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so it's like 1.65 second. Okay, so we're done with data table 12a.1. Okay, pendulum length was constant. Now we'll take a break for 1 second. Let's set up for the second data table. Yeah, I'm back again. Now table 12a2. Okay, we'll increase the mass 100, 200, 500. Length remain the same. We did not change the length, and it is the dependence of the period on mass. Okay, so here you go. Let's start here. Okay, and here's my protractor. Angle is fixed 20 degrees. So every time we do it, it is at 20 degrees. Angle is constant. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if you divide time, it comes out 1.532. By the way, don't worry, I'm going to give you the table and I'm just showing you. Okay, so now mass is 200 grams. Here we go. 200 and clear, and again 20 degrees. Again 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so the time is 1.559 second per oscillation. Now 500 grams. Oh. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so it's like 1.57 second period. Okay, here we go. I'm going to make it 10 degree, 20 degree, right? The difference. Okay. First one will be a little difficult, but we'll see. Okay. Two, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So it's like 0.6 second. Oh, 0.6 second. Okay. And then we okay, I'm ready. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So it's like 0.868. Okay, now 40 centimeter. Okay. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's like 1.22 second. Now it is 60 now. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 1.61 second. Okay. Now the 80. So 1.78. Okay. Now the last one will be a meter. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's like 1.95 second. Okay. So that concludes this part of the experiment, part A we have done. Okay, thank you. I'm back again with the part B. Okay, if you look at page 7, okay, table 12B1. Okay, you see there's a spring here. We have to calculate the spring constant. A similar experiment you have done in lab 7. Remember? Okay, so I have already done the experiment just to show you. First, if you look at table, first look, no mass here. So the total suspended mass is 0 gram, okay, and total suspended weight would be 0 Newton, and elongation would be 0, right? Let me show you if I hang 50 grams, okay. This is 50 grams, okay, which is 0.05 kilogram multiplied by 9.8, which is 0.49 Newton. Okay, remember? So here, and if you measure the elongation now, okay, so if you take here and you read from here, so it's like total elongation, remember it is like 10 centimeter, about 12, about 12, okay, so it's about 0.012, look at 0.012 meter, okay, 1.2 centimeter, which is 0.012 meter, okay. So we did that, then we hang 100, okay, and we come out 0.029 meter, 450.047. Let me show you. I put 300 just to show you, okay, the elongation. So remember here 0, now 300, okay, which will be this, okay, and this, okay, so which comes about 0.098 meter. Full. So then you plot all this data. I'll give you the data. You plot, find the slope of the graph, which will be spring constant K. Okay. So for table 12B1, that is the experiment. Okay. So I hope everybody got it right. Instead of doing all in front of you, I have already done and got the data point. I'll provide this data table. You draw the graph. 12B2. Let's move on there. Okay. Here, we're going to calculate period of oscillation, okay, and you have, if you look at the table, M1 50 grams, M2 100 grams, M3 200 grams, M4 300 grams, M5 350 grams, okay. Now you measure the time, okay, total time, and then number of oscillations, okay, divide that time by the number of oscillations, you get the period, and then you square it if you look at your table, okay. So here the way to do it, okay, so 50, you put it here, okay, and you take it away from here, okay, and then when you push it down, not much, you will see it will be chaotic, okay, and normally we use, so that the weight doesn't fall off, we tape it, this is the slotted mass, okay, otherwise it will fly away, okay. So here you go, the way we do the experiment, here you go, look, you put it here, okay, and then, okay, and this, you don't have to do very much, and if you look at here, just go as minimum as possible, okay, here, and then let it oscillate. See how chaotic it becomes. See, look. So to avoid that, normally what we do is just put it down, okay. So here you go. Let's look at. You start your stopwatch, okay, and you just let it go. So I'm going to do 19 oscillation, okay. Here you go for this one. Oh, I'm sorry, I didn't start it. I'm sorry. Here you go. At the same time, you have to start. Okay. So 19, it comes about 5.47 seconds. So what do you have to do? 5.47 seconds divided by 19 will be the period of oscillation. Okay. So now you do it, and then M2 is 100, so you take it out. You put 100, okay, close it, okay, and then this time we did 14 when I do that, because otherwise it becomes chaotic, and okay, and then the total time we got 5.5 seconds, okay, for 14 oscillations. So the period is 0.393 seconds we calculated, okay. So then 200, then 300, and then 50, and I tabulated the data for you, okay, and I'll post it, okay, in appropriate time for you, okay. So this is part B, okay, everybody, and then okay, and I believe that is the experiment, okay. So I'll give you all the data and the calculation for period square. All you have to do, graph and answer the questions, okay. So we are done with this experiment, okay, good, thank you.